Erdish was a legend. He was alive during your life, so he brought a lot of people into mathematics. Just a generous human being. I'm trying to get Dr. Cutler in to give a talk here as on Ramsey theory. We'll see what he goes. The difficulty for us is that 7:40 start time. Most mathematicians do not like to get up that early. So we'll see what happens. He is on the East Coast, so maybe mathematicians on the West Coast would be better. They haven't gone to bed yet. All right, from last class, if you weren't here, I did ask you to catch up on this and watch the videos. If you're doing it this weekend, some of this is going to seem unfamiliar. But I'm going to show you today what's referred to as the party problem. You might have heard of it before. The question is, if you have what's a minimal number of people that you would need at a party to guarantee you either have 3 mutual strangers or 3 mutual friends? So if you think about it, if you have a really large party, well, it's going to kind of seem obvious that you're going to have 3 people who all do not know each other or 3 people who all do know each other. So the question is, how do you whittle that down and find that one number where it's exactly, this is it, this is the sharpest point? And so that's what these, go ahead.
Is this like 3 people to you or 3 people like at the party?
At the party.
Okay.
So we call them cliques. It's not the cliques that you think of in high school, but it's CLIQE. It's a clique of people who all do not know each other mutually. Mutual strangers or mutual friends. So they all 3 know each other. So it seems reasonable that if you jack up the number of people at the party, this is going to happen. What you want to know is what's that minimal amount that you'd have to have. This is called the Ramsey number of 3, 3. And so you're looking for what Ramsey number of 3, 3 is equal to. At the very top, I put Erdish's quotes. There's actually a site that is attributed to all kinds of Erdish quotes. I got it wrong. It's not a demon, it's an alien. But the spirit of what I said the other day is there. 3, 3 is super easy. I'm going to prove it for you using pigeonhole principle. But I used to prove it in a Math for Poets class where students who don't like mathematics took that class as their general education requirement, and I'd prove it just by case. And so they did understand it. They'd even write on Rate My Professor, this is not real math. It's as real as you get. Like, this is real math. Funny thing, a lot of the things you guys do here are not thought of as real math in the math world. So I keep sending more cadets to give talks there. So
the Ramsey number is the party problem?
The Ramsey number of 3, 3 is how many people do you need at a party to guarantee you have a clique of 3 people who all mutually know each other or 3 people who all mutually don't. This is also called you can all do the same question for 4, 4. How many people do you need at a party to get a group of 4 people who all know each other and a group of 4 people who all do not know each other? So you could ask that same question. So the party problem is more general. Good? Okay, so it turns out that it's 6 for R33. I'll show you at the end that these are open problems. It'd be nice if Dr. Cutler can come and show you how to kind of fool around with these problems. R44 is known, R55 is not known, R66 is not known. So there's a few of them that these are super hard problems. They don't seem like they would be, especially because I can prove R33. So it's pretty simple. You start with person 1. And just to recall, the generalized pigeonhole principle says that if we partition a set with more than k times n elements into n blocks, then at least one block is going to have k plus 1 elements. So if you think of person 1, you can pull out any person, but just like person 1 is out to the side. And you start drawing lines between them. If I try to partition this extra piece into 2 pieces, then at least one of those partitions is going to have an extra person. So you can go, it's really a case-by-case thing, right? So either person 1 knows person 2, and person 2 knows person 3. So you can go through case by case, but really pigeonhole principle gives it to you all at once. Because if you try to split this group up into strangers and friends, what's going to happen is that you're going to get two pieces that are strangers and friends, and that means that at least one of the partition group would have to be of one kind. One group would have to be of one kind. There's no way to get around that because of pigeonhole principle. In other words, person one will still have at least three people who are mutually friends or mutually strangers. So if I just start drawing lines, let's suppose they're all strangers. Well, then I'm done. If they're all strangers to each other, then I'm done. So this is how I prove it for that Math for Poets class. I just say, okay, what if? What if they were all strangers? Well, then I'm done because I have a group of three mutual strangers. But then I could have four friends. And they're all friends with each other too. So if that happens, well then I'm done too, because then three of them are all mutual friends. So you just go through case by case, and you realize by pigeonhole principle, there's no way to rack and stack this without having something drip off. Like when you try to pull the rug into the direction of all friends, you're going to have a clique of all friends. If you try to pull the direction of all strangers, you're going to have enough strangers. So the cusp is right at 3 and 3. You're going to have a group of all friends and three group of all strangers, and you can't get beyond that. So I'm just drawing out the cases for you.
Wait, since we don't know it's 6 to begin with, why are we using 6 people?
Well, you're trying to prove it's 6 people. So you can pick out. The way this kind of math works is you come up with a good conjecture. So I'm guessing that it's 6, and then I'm proving it. So I'm not assuming what I'm trying to prove. I have to prove it still. I don't know if Dr. Pillyblank has talked about this problem in graph theory, but this is the classic problem for graph theory, and you would actually draw the graph, and I'm going to have you guys do that actually. So if you think about it as a graph, which board can you guys see the best on? That side? Can you guys see over there? Okay. So if you think about 6 people, 1, 2, 3, 4, 5, 6, and draw them around in a circle. Well, you can just start drawing lines from one to the other and say they're friends, or just kind of like I'm doing here with person 1. You can say this is person 1, and say I know that case 1, these guys are strangers, and these guys are friends. So dash would be friends, and solid would be strangers. 2 colors is what we would use. And then you start drawing all possible combinations of lines. You can actually do that. It's not that hard to do. And to be a clique, you have to be a triangle of one color. And so when you start drawing all these cases, it turns out that no matter how you draw it, you will get a solid triangle or you will get a dashed triangle. It's not going to work any other way. So this is another way you can see it with a graph. So has he talked about that in his class?
We did like another sort of party problem, but I don't think it was this exact one.
Yeah, these are the classic. Like every time we try to hire a common torch, they say, "Well, my goal in life is to solve Ramsey 5-5." They always come and say it's such a classic problem. You guys can ask him about it today. The Ramsey number, how close we are. He'll know everything about that because that's his field. So I'm just doing the 2 colors with one person, but I would just start drawing all the possible lines to each person and then shading it. Either they're friends or they're strangers, and you start drawing all these colors from one person out. But this argument for person number 1 by generalized pigeonhole principle works for all of them. So if you start drawing the lines from all of them, it's going to be the same case. There's no way to partition up the group of friends and strangers without ending up with a clique, a triangle.
For this like for this right here, we know that person 1 and 2 are strangers and 1 and 3 are strangers, but how do we know that 2 and 3 are strangers?
You don't. You have to work out each cases. But what the generalized pigeonhole principle tells you is there's no way to partition that without having one of those groups have more than one clique in it.
Okay.
Right? That's what it says. This is really partitioning out by cliques. So really, it is a case-by-case theorem, even if you're using generalized pigeonhole principle to make that argument. You really are doing it case by case. So literally, when I taught this in the Math for Poets class, I would actually go through each case, and and then I'd have them run some cases so that they get the hang of it. And we could do that. So this doesn't prove that it's 6. This just says it might be 6, right? If you end up going through all cases, it could be 5. Step 2 is to make that conclusion. The partition will always give us 3 or more mutual strangers or 3 or more mutual friends. There's no other way around it. You can try it. I'd like you to try it with coloring and vertices, just like I did over here. Start drawing all those connections and see if you can get it to not work. Basically, you're assuming it's not 6, and then trying to get it to come out so that you can't. You'll see that it will work. So let's say if I start randomly, you can do it also in an ordered way, and so you're cataloging all your cases. Like that could happen, this could happen, this could happen. So if you start, I'm just randomly doing it. Well, I have these. I'm going to put a dash. I'm going to try to force it not to work. Now, if I put a dash line here, I've got a triangle. If I put a solid line here, I've got this triangle. So there's no way around it. So you'll see when you get to the end, you will end up with a triangle. So try to force it so that you can't get a triangle of one kind. A triangle means that they're either 3 friends, call it whatever you want. Friends, strangers. So if I put a dash line here, now I have a group of 3 strangers. If I put a solid line here, I'm also done. I have a group of 3 friends.
What is the rule? You have to have one line going to each.
Yeah, everybody's either a friend or a stranger. There's only 2 possibilities, right?
So should every dot have?
Yes,
6 lines?
but I don't need to finish it at this point. Like I know that what I've drawn here, I'm kind of done.
Do you have triangles?
Yeah, once I have a triangle, I'm done, right?
Oh.
And so try to force it so it doesn't have a triangle in it, and see if you can get it to be violated. And you can see because of the symmetry of the way I've drawn it, I really only have to worry about the directions it's going from person 1. Because I just have rotate the whole thing and do it again with person 2.
Wait, so that would be, without finishing it, that would be an incomplete graph, but it's
Yeah, I can finish it if you want.
Well, oh no, I'm just asking, it's just not complete because all the dots don't have 6 lines coming from it. Right?
Yeah, you'll have to complete it all. This one has that one. Since I did this completely randomly, now I'm in trouble because I have to figure out where I don't have a line going from something. It would have 5 lines emanating from it, right? Each dot would have 5 lines emanating. It's the picture I made earlier with the person 1. You'd have 5 lines going out.
You try to avoid the triangle and 3 solid lines or triangle.
You're either one. So try to avoid either one from happening and see if you can get it to. You saw that I got in trouble right away. I was like, okay, now I'm screwed because if I put a solid line here, I have a triangle, and if I put a dash line here, I have a triangle.
So if it's a mix of solid and dash, then.
Yeah, if you can get it to not have a solid triangle or a dash triangle,
Or a solid and dash.
then you've disproven that it's 6. You've come up with a counterexample.
So solid and dash works as a.
Yes, if you can find that an example where you have a complete graph like this and you don't have a triangle in it, then you have a counterexample. So try to see if you can get that counterexample.
And how many graphs are there for 6 nodes like that?
It would be if you think of person 1 and 5 lines emanating from it, and there's 5 different. So it'd be 5, choose 2 coming out. So it really comes out to counting.